The perfect design of the universe, too. Hello everyone, and welcome to my channel. From the delicate balance of the four fundamental forces to the just right density of stars in the Milky Way, from the crucial role of interstellar dust in the birth of stars, to the subtle collaboration of the strong and weak forces in the nucleus of an atom, every detail makes one wonder if it is all really a coincidence. Every fundamental constant of the universe, every value of the laws of nature, seems to inadvertently create the most ideal conditions for the birth, evolution, and prosperity of life. Is there an invisible force manipulating behind the scenes, carefully adjusting everything? Or is the perfect design of it all the very wonder of the universe itself? Today, we will explore 8 perfect designs of the universe together. 11. Parameters of strong, weak, electromagnetic, and gravitational forces can support the formation of complex structures. The 4 fundamental forces of the universe, the strong force, the weak force, the electromagnetic force, and the gravitational force are at the heart of the design of the universe, supporting the structure of the entire universe, the formation of matter, and the existence of our life. Simply put, they are the programming language of the universe, determining how all matter behaves and allowing life to be born and evolve on Earth. Before we discuss the effects of these forces, let's quickly review these 4 forces. 1. The strong force, also known as the strong interaction force. This is the strongest force in the universe. It acts inside the nucleus of an atom and is responsible for holding protons and neutrons together. Imagine if there is no strong force, the protons, positively charged, in the nucleus would repel each other because they have the same electric charge, and the attraction between protons and neutrons is realized by the strong force. 2. Weak force. It is the force that affects particle decay and nuclear reactions, such as in the hydrogen fusion reaction that occurs inside the Sun, where the weak force plays a crucial role. It is much weaker than the strong force, but under certain conditions, its role cannot be ignored, especially when it comes to radioactive decay and particle conversion. 3. Electromagnetic force. This is the most familiar force in our daily life and is responsible for the interaction between charges. Positive and negative charges attract, similar to the attraction and repulsion of an electromagnet, is a manifestation of the electromagnetic force. Electromagnetic force not only shapes the structure of atoms, but also the way light and electric waves travel. 4. Gravity is the weakest but most widely acting force, which acts between all objects with mass. Gravity determines the motion of planets, the stability of planetary orbits, and even the structure of entire galaxies. Although it is much weaker than the other 3 forces, its effects are significant because of its ubiquitous nature. These forces are like the 4 great artifacts of the universe, which influence the behavior of matter in different ways, and the world we live in is actually the result of the joint action of these 4 forces. Although each of these forces has a different role to play, their strength and range of action, what we call parameters, are crucial to the formation of complex structures. The universe we live in relies on the parameters of these forces working together in just the right way to make what we see today possible. To make it easier for you to understand, we can put it in an interesting perspective. If you're designing a high-rise building, the strength of the building materials, the spacing of the columns, and the distribution of weight are all critical. If the density of the steel and concrete is not right, or if a certain structure does not have enough weight-bearing capacity, then the building might collapse. The universe is similar in that we are living in an extremely complex building, whose building materials are determined by the parameters of these forces. For example, if the strength of the force is too strong, the nuclei of atoms will be too close to each other, and the elements may not be able to stabilize the existence of the composition of life. If the gravitational force is too strong, it may lead to the collapse of the stars, and the universe will become too dense, and all the matter may be in a moment of the Big Bang and not be able to form a complex structure. Let's start with gravity. Although gravity is the weakest of the 4 forces, it is the foundation of the entire universe. Without gravity, galaxies, planets, and stars would not be able to come together, and the matter in the universe would be scattered. You can imagine that gravity is like the glue in the universe that holds all objects and matter together. The importance of gravity lies not only in its influence on celestial bodies, but also in its role in the formation of the large-scale structure of the universe. The formation of galaxies is a typical example. As gravity acts, gas and dust dispersed throughout the universe gradually builds up into nebulae, which eventually form stars and planets. If the gravitational force were stronger, the stars would overgather, and the excess gravity would cause the stars to collapse and form black holes. Conversely, if gravity is too weak, galaxies may not be able to form as complex a structure. And at the right strength of gravity, it happens to support the formation of star systems and galaxies, as well as giving planetary systems stable orbits. The process of solar system formation is a good example. The gravitational relationship between the Sun and the planets is just right to keep the Earth and the other planets in suitable orbits, not colliding with each other because the gravitational force is too strong, and not falling out of orbit because the gravitational force is too weak. Next is the electromagnetic force. The electromagnetic force has a very wide range of effects and influences, and it not only determines the basic properties of matter, but it also influences the chemical reactions that take place. Think about it. All molecules and atoms are affected by the electromagnetic force. In the case of water molecules, the chemical bonds between the hydrogen and oxygen atoms in a water molecule are formed through the action of the electromagnetic force. The electromagnetic force allows stable chemical bonds to be formed between atoms and molecules, which in turn form complex molecular structures under the right conditions. And these molecules in turn form the substances needed for life through chemical reactions. If the parameters of the electromagnetic force are changed slightly, for example, if the charge strength is too weak, the bonds between atoms will not be strong enough to stabilize the molecules, while if the charge is too strong, the chemical reactions may be too violent, and the equilibrium required for life cannot be maintained. Therefore, the strength of the electromagnetic force must be just right in order to support complex chemical structures and thus the birth of life. The strong force and the weak force are responsible for the internal structure of the nucleus and the decay of particles, respectively. The strong force is the strongest force in the universe and acts between protons and neutrons, allowing these particles to bond together securely to form stable nuclei. Without the strong force, protons and neutrons would not be able to maintain a stable bond, and nuclei would not be formed. But the strong force is not omnipotent. If the force is too strong, the energy inside the nucleus can become too concentrated, resulting in the elements not being able to fuse in the proper way, and the heavy elements necessary for life may not be stable. On the other hand, if the force is too weak, the nucleus will not be able to form a stable structure, and the chemical elements will not be able to exist for a long time. Therefore, the moderation of the strong force is crucial for the formation of complex structures. As for the weak force, although it is much weaker than the strong force, it plays a key role in the decay of particles and some nuclear reactions. The weak force can cause some particles to change into other forms, which provides an important conversion mechanism for some elements in the universe. For example, nuclear fusion within the Sun relies on the weak force, which helps transform hydrogen atoms into helium atoms while releasing enormous amounts of energy, providing the Earth with the energy it needs for life. Through the interaction of these four forces, the structure of the universe is stabilized and the conditions for life are met. Each parameter of the forces seems like a cosmic dispatcher, and they work skillfully together in the context of a vast spacetime to build the vibrant world before us. As physicist Stephen Hawking once said, the constants and natural laws of the universe are precisely designed, and these laws create the environment in which we can live. In fact, scientists have discovered that these fundamental force parameters of the universe coincide with the conditions under which life can be born and continue to evolve. If the values of these forces were to deviate even slightly, life on Earth could not exist. These four great artifacts of the universe work together to support the order of the universe and the possibility of life through precise parameterization. 12. The role of black holes. Black holes are not just all-devouring beings, they play a much more complex and far-reaching role in the universe, especially in the formation and evolution of galaxies, and even in the origin of life. First, we need to understand the basic properties of black holes themselves. A black hole is an extremely dense mass of matter with a gravitational pull so strong that not even light can escape it. This is why we call them black holes. At the core of a black hole, the spatial and temporal structure of matter and space becomes extremely distorted at a point called a singularity, which cannot be fully described by our current physical theories. According to the predictions of general relativity, any star of sufficient mass will collapse at the end of its life cycle as a result of the cessation of internal nuclear reactions. This collapse could eventually lead to the formation of a black hole. Black holes are surrounded by a boundary called the event horizon, beyond which no matter or information can return, making them one of the most mysterious beings in the universe. However, black holes do not just swallow everything as their name suggests. In fact, black holes not only have a huge impact on the universe around them, but they also work and play an important role in the universe itself. In fact, almost every large galaxy has a supermassive black hole at its center. In our galaxy, the Milky Way, for example, the supermassive black hole at the center of the Milky Way, known as Sagittarius A*, has a mass about 4 million times that of the Sun. Scientists used to think that these supermassive black holes were mainly giant voids in the universe. That is, they just attracted matter around them, but did not affect the overall structure and evolution of galaxies. However, research in recent years has disproved this idea. A growing body of evidence suggests that black holes are more than just cosmic dumping grounds. They may be the central driving force behind the formation and evolution of galaxies. One interesting phenomenon is that the formation and evolution of supermassive black holes and their host galaxies seem to be closely related. In other words, the size and shape of a galaxy, and even the distribution of its interstellar material and stars, may be closely related to the presence and mass of black holes and their activities. Scientists have hypothesized that black holes may influence the process of galaxy formation through a feedback mechanism. This feedback mechanism can occur in two main ways. First, through the strong gravitational pull of black holes, which directly affects the distribution of material in galaxies, and second, through the ejective activity of black holes, which releases a large amount of energy and material, which, in turn, affects the formation of gas and stars in galaxies. 1. The role of gravity. The gravity of a supermassive black hole is so powerful that it can change the structure of galaxies by means of gravitational waves, the formation of matter accretion disks, and even the accretion of interstellar gas around the black hole. For example, the material around a black hole may be attracted to the interior of the black hole, forming a huge accretion disk, and the material in such a disk will often release a large amount of radiation before it is swallowed up by the black hole, becoming the so-called active galactic nuclei (AGN). This radiation can heat up the surrounding gas and inhibit the formation of new stars. 2. Feedback mechanism. Black holes not only consume matter, they also feed energy back into the galactic environment by ejecting matter. This ejection of material is often referred to as jets or bubbles. By observing these jets, scientists have found that the jet activity of black holes inhibits the cooling of the gas inside galaxies, thus reducing the birth of new stars. This feedback may explain why some galaxies, despite their abundance of gas and matter, no longer form new stars or form stars very slowly. Black holes don't just play a role in the formation of galaxies, they also act as energy providers within galaxies. For example, a supermassive black hole in its active phase will continuously accrete material around it, which will form a high-speed spinning accretion disk before approaching the black hole. Due to the friction and compression effect inside the accretion disk, the matter will heat up rapidly and produce huge radiation. This radiation is not only visible light, but also high-energy radiation such as X-rays and gamma rays, which can even span millions of light years and affect other parts of the galaxy. Even more amazingly, black holes eject some of their energy in the form of jets as they accrete matter. These jets are sometimes so powerful that they form beams of particles that can be ejected to the outside of the galaxy at speeds close to the speed of light. These jets are not only a form of energy release from the black hole, but they can also drive the flow of gas and matter around them, and even affect the overall evolution of the galaxy by blowing away the surrounding gas. Let's take an example of this jet process. Astronomers have observed that the super black hole in the galaxy M87, located near the Milky Way, has jets that are so powerful that they span almost the entire galaxy. These jets have been observed to travel across distances of millions of light-years, affecting the distribution of gas in the galaxy. M87's black hole jet was in the spotlight in 2019 when scientists managed to capture an image of it through the Event Horizon Telescope, EHT. The image shows extreme details of the black hole's shadow and jet stream, not only validating the black hole theory, but also opening a new window into the physics of the universe. The exchange of energy and matter by black holes doesn't just affect individual galaxies. Their effects may also have implications for the evolution of the entire universe. For example, scientists once asked the question, if there are more and more supermassive black holes in the universe, will they merge one day, eventually leading to a black hole era for the entire universe? This scenario is based on the study of interactions between black holes. Over time, black holes and galaxies may come closer together due to gravitational waves and eventually merge, releasing large amounts of energy. And as these black holes continue to merge, the structure of the universe may change. More extreme speculations suggest that the universe may enter a black hole-dominated state, i.e., a black hole universe, where almost all matter is swallowed up into the black hole, and all that is left is the immense gravitational force and dark matter. 13. Nuclear fusion in stars. Nuclear fusion in stars is the mysterious factory of the universe's lifeblood. What is nuclear fusion? Simply put, fusion is a nuclear reaction inside a star that combines lighter nuclei into heavier ones and releases a lot of energy. Think of it as a kind of cosmic factory where the star makes elements through fusion and releases huge amounts of energy, which spreads out into space in the form of light and heat, lighting up the universe. So how exactly do stars utilize the process of nuclear fusion to allow us, seemingly unrelated objects and life, to exist? The fusion journey of stars begins with the simplest element, hydrogen. Almost all stars, including our Sun, use hydrogen as their main fuel. Inside a star, the temperature is millions of degrees and the pressure is extremely high. In this extreme environment, hydrogen nuclei, i.e., protons, are compressed together by the strong gravitational force and begin to undergo a fusion reaction. Through this fusion reaction, the hydrogen atoms combine to form helium atoms. The energy released by this process is the source of a star's brilliance. Every star undergoing hydrogen fusion is actually consuming hydrogen, transforming it into heavier elements, and through this reaction releasing enormous amounts of light and heat that illuminate the cosmic space around it. The Sun, for example, is a typical hydrogen fusion reaction factory. At the core of the Sun, about 60 million tons of hydrogen are converted into helium every second, while releasing countless photons of light that travel for millions of years before they are finally released from the surface of the Sun as the sunlight we feel. As stars live on, they begin to consume the hydrogen inside them. Once they run out of hydrogen fuel, the core of the star begins to collapse, increasing the temperature and pressure even further. At this point, heavier elements also begin to fusion inside the star. When the star's core reaches a temperature of about 100 million degrees, helium atoms begin to fusion, forming heavier elements such as carbon and oxygen. These elements are the basic building blocks of life. Carbon is at the core of all organic matter on Earth, and oxygen is needed for most living things to breathe. Therefore, stars are not only a source of energy, they are also the chemical factories that build the materials for life. Not only that, but as stars evolve, they further synthesize heavier elements. For example, more massive stars continue to convert carbon into heavier elements such as magnesium, silicon, and even iron through nuclear fusion reactions. The formation of iron marks the end of a star's life. When the star's interior is nearly out of fuel, the star's core undergoes a huge eruption. For more massive stars, this eruption is called a supernova explosion. Supernova outbursts are one of the most magnificent and violent events in the universe and can release more energy than even an entire galaxy in all its glory. During this supernova outburst, the outer layers of a star's material are violently ejected into space, creating a huge shock wave. At this time, the elements that were originally inside the star, including iron, magnesium, silicon, carbon, etc., are ejected into the universe at high speed. This process is like a huge chemical bomb. Through the supernova explosion, the universe rich in heavy elements can be spread to all corners. These elements provided the raw materials for the birth of subsequent galaxies, planets, and even life. In fact, most of the elements on Earth, especially all the elements heavier than helium, were made only through supernova outbursts. So, in a sense, we could not exist without the stars that once exploded in the universe. You may be wondering how the energy of nuclear fusion in stars, which is used primarily to keep them bright and warm, affects the formation of planets. In fact, nuclear fusion powers everything around us, and this energy is not limited to the star itself. It also indirectly influences the birth of planets through the process of star formation. The process of planet formation usually occurs at the same time as the birth of a star. As the star forms, the gas and dust around it will also begin to accumulate, gradually forming a planetary disk. After the star's fusion reaction begins, the radiation and storms that are released affect the distribution of this gas and dust, which in turn affects the process of planet formation and evolution. We can think of this process as an interstellar chemistry experiment in which the star, through its own radiation, storms, and fusion processes, drives the transformation of the surrounding material, ultimately forming planets like Earth. How do these elements relate to life? The chemical elements needed for life on Earth, including carbon, nitrogen, oxygen, and phosphorus, are born in the very nuclear fusion reactions of stars. They are gradually synthesized over the life cycle of the star and released into interstellar space as the star dies. These elements are distributed to all corners of the universe in the form of dust and gas clouds, and eventually become the raw materials for planet formation. More importantly, these elements from nuclear fusion may have provided the basic building blocks for the origin of life. Amino acids, proteins, DNA, and other basic materials of life on Earth were all synthesized by these elements in a special environment. In fact, by studying the chemical environment of the early Earth, scientists have discovered how these interstellar elements were involved in the birth of life in the early Earth environment. 14. Stability over long timescales. We often lament the passage of time, both in human lifetimes and in the rise and fall of civilizations. The timescale of the universe is far grander than we can imagine. And it is the stability of this extraordinarily long timescale that has given the stars, planets, and even life in the universe enough time to undergo the complex evolution that has culminated in the wondrous world we see today. You may have heard the saying, the universe is 4.5 billion years old, while the Earth is 1 billion years old. The two may seem close, but in reality, they are vastly different. The universe, as we know it, began with the Big Bang, and today some 13.8 billion years have passed. In comparison, the Earth is only about 4.6 billion years old, and the history of human civilization on Earth is less than a few thousand years. One can imagine how many earth-shattering changes have taken place during this long span of time. Consider that at the beginning of the universe, the temperature was almost infinitely high, and all the matter and energy were densely concentrated in a very small space. However, after the Big Bang, the universe began to expand rapidly, gradually cooled, and matter began to gather in different forms to form the galaxies, stars, planets, and even life we see today. The evolution of the universe, from a primordial ball of fire, to the birth of stars, the formation of planets, and the emergence of life, has spanned such a vast time scale that it has given stars, planets, and life enough patience to carry on with their complex evolution, and may even continue to evolve in the future, taking on more forms than we can even imagine. The life cycle of a star is itself an example of a complex evolutionary process. The life cycle of a star is itself a classic example of the cosmic timescale. Let's take the Sun as an example. It is about 4.6 billion years old, and scientists predict that it will burn steadily for about another 5 billion years. In other words, the Sun existed before the birth of the Earth, and it will continue to shine on us for billions of years until it eventually enters its death phase. The evolution of a star begins at birth and goes through several stages. First, hydrogen is gravitationally accreted and compressed around it until the temperature and pressure are high enough for the hydrogen fusion reaction to begin, resulting in light and heat. Then, as the hydrogen is consumed, the star enters the red giant stage and begins to burn helium or even heavier elements, and finally, some stars explode into supernovas, forming black holes or neutron stars. And those smaller stars, such as the Sun, turn into white dwarfs and gradually cool down and disappear. The process is so long that over billions of years, stars go through multiple phases of burning, expanding, contracting, and exploding, each of which relies on an extremely fine balance and stability. For example, during a star's stabilization period, the hydrogen fusion energy in the core is just enough to counteract the external gravitational pull and maintain the star's shape and light. However, once this balance is broken, the star enters a different stage of evolution until its eventual death. All this depends on the stability of the universe. In other words, the existence and evolution of stars are based on the stability of the universe on a long timescale. The lifespan of a star is a small part of the universe's timescale, but it is this time that constitutes the most important source of energy in the universe. If the stars are the burning embers of the universe, then the planets are the dancers that jump around these embers. The process of planet formation is also entirely dependent on the ultra-long timescale of the universe. The birth of the Earth, for example, can be traced back to about 4.6 billion years ago. At that time, the clouds of gas and dust in our solar system gradually contracted and rotated, eventually forming the planets, including the Earth, under the force of gravity. The evolution of the planets has been equally long and complex. From the initial cooling and formation of the Earth's crust, to the creation of an atmosphere, to the birth of life, each step took hundreds of millions of years to complete. Phenomena such as continental drift, climate change, and species evolution on Earth have all occurred on this extraordinarily long timescale. The evolution of life on Earth is like an epic poem spanning billions of years, from the first single-celled organisms to the complex and diverse life forms of today. This process is not only the result of natural selection and mutation, but also the product of the interweaving of countless chance events and environmental changes. According to existing scientific theories, the origin of life on Earth occurred around 3.8 billion years ago, and although the exact timing is uncertain, it is generally accepted that life originated from simple chemical reactions on the primordial Earth. The early Earth was very different from today. There was no atmosphere, the surface was extremely hot, volcanism was high, and frequent meteorite impacts caused temperatures on the surface to reach thousands of degrees at times. About 4.5 billion years ago, the Earth gradually cooled down and water vapor condensed into water, forming the atmosphere and oceans. Scientists hypothesize that the origin of life may have been in the oceans at this stage, where specific chemical conditions and sources of energy, e.g., lightning, volcanic activity, ultraviolet radiation, etc., gave rise to the first organic molecules. The basic building blocks of life are organic molecules, especially amino acids, fatty acids, and nucleotides. These organic molecules were probably formed through a series of chemical reactions. Scientists have successfully synthesized a variety of amino acids by simulating the environment of the early Earth through the famous Miller-Urey experiment, 1953, which provides strong evidence of the chemical processes that led to the origin of life. These organic molecules may have accumulated in oceanic shoals, hot springs, or other energy-rich environments. Over long periods of time, they interacted with each other and gradually formed more complex molecular structures, such as RNA and DNA, which not only stored genetic information but also catalyzed chemical reactions, marking the transition from simple chemical reactions to preliminary life forms. The true birth of life is thought to have occurred on the basis of a series of chemical reactions. These simple organic molecules may have formed early primitive cells through self-assembly. About 3.8 billion years ago, the earliest single-celled organisms began to flourish in the waters of the Earth. About 3.5 billion years ago, the first photosynthesizing organisms, blue-green algae, or cyanobacteria, appeared on Earth. Blue-green algae marked a new stage of life by converting sunlight, carbon dioxide, and water into oxygen and glucose through photosynthesis. Their appearance changed the composition of the Earth's atmosphere, paving the way for the later birth of complex life. About 2 billion years ago, eukaryotic cells first appeared. The appearance of eukaryotic cells was a major leap forward in the evolutionary history of life. After single-celled organisms had flourished on Earth for hundreds of millions of years, multicellular organisms began to appear about 1 billion years ago. Multicellular organisms consist of multiple single cells that cooperate with each other in specific ways to form complex tissues and organs. The emergence of multicellular organisms led to a huge expansion of organisms in terms of body size, structure, and function, providing the basis for subsequent diversity. By 600 million years ago, the first animals appeared in the Earth's oceans. They were simple sponge-like organisms with simple body structures, but they had begun to have some organization and function. It happened about 540 million years ago, and during this period, the diversity of life on Earth increased dramatically, with almost all extant animal phyla appearing during this period, and the complexity and diversity of life rapidly increasing. Over time, the arena of life gradually expanded from the oceans to the land. About 460 million years ago, the earliest land plants, whose ancestors were probably aquatic algae, began to appear on Earth. Amphibians were the first vertebrates to successfully make their way onto land. About 360 million years ago, some fish acquired, through gradual evolution, features adapted to life on land, such as hard scales, lungs, and limbs capable of respiration. Mammals first appeared on Earth 200 million years ago. They were distinguished from reptiles by features such as breastfeeding and constant temperature. With the extinction of the dinosaurs, mammals gradually multiplied and eventually evolved into the more intelligent species, humans. Why, you may ask, did it take such a long span of time to support the evolution of life? It is precisely because the universe gave it enough time. These evolutionary processes are extremely complex and full of changes, and each small change can have a profound effect on the entire ecosystem. For example, the Earth's climate has changed dramatically at different times in history, from cold ice ages to warm modern climates, and all these changes have provided different opportunities and challenges for the evolution of life. The universe has given the Earth stable conditions that have allowed life to evolve over billions of years, constantly responding to changes in the environment and adapting to new challenges. Every mutation, every change in species, is the result of accumulation over billions of years. The biodiversity we see today is actually the product of a long period of stable environments and the accumulation of time. So why is the long time scale so important? Not only does it provide ample evolutionary space for stars and planets, but it also provides opportunities for complex changes and trial and error in the evolution of life. If the time scale of the universe were much shorter, the evolution of galaxies, stars, planets, and even life might not have been successfully accomplished at all. In the case of life on Earth, if the Earth's environment and climate were to change too drastically, the evolution of life could not be sustained and early organisms could become extinct due to their inability to adapt to their new environment. One study has shown that if the Earth's climate changes drastically at some point, resulting in a sharp rise or fall in temperature, life may not be able to adapt to this environment, and it may even lead to mass extinction. The slowness and continuity of such changes is also brought about by the stability of the universe on ultra-long timescales. Life is able to adapt to environmental changes and evolve gradually because these changes occur very slowly. If you look at it from the perspective of the universe, the Earth may be one of the lucky ones. In this huge universe, there are stars and planets all over the place, but it is rare for a planet like Earth to have such a stable environment that supports life. The reason why we can survive, reproduce, and evolve here is that the universe provides enough space for the birth of life on such a long time scale, not only space and time, but also environmental stability. Scientists have also been searching for traces of extraterrestrial life, especially in galaxies and planets that are similar to Earth. There may be thousands of Earth-like planets in the universe as we know it, and they may have similar conditions for the origin of life, but it will take time to prove whether or not intelligent life can eventually evolve. 15. Orbital resonance of celestial bodies. Have you ever thought that the movements of celestial bodies are like a grand symphony? Each planet, each moon, each star bounces and rotates in its own orbit, but they do not move in isolation and are often stabilized by a wonderful resonance with each other. This phenomenon is called orbital resonance. At this point, you may ask, what exactly is this? Is it just a beautiful sight like we see in the stars? In fact, this resonance relationship is crucial to many celestial systems in the universe, not only affecting the orbital stability of these objects, but also making the entire universe appear to operate in a more refined and harmonious manner. First, let's bring the conversation back to Earth and assume you're playing a musical game with your friends. If you keep the rhythm of your music in unison, you create a harmonious melody. If your rhythms are not in sync, the music will seem chaotic. Orbital resonance between celestial bodies is really like this rhythm game. Resonance occurs when the orbital periods of two or more celestial bodies are related with some regularity, like the beat that bounces between them in the universe. Simply put, orbital resonance is the relationship between the orbital periods of two or more objects in integer ratios, i.e., their rotational periods match each other in a particular ratio, thus stabilizing their orbits. For example, if there are two planets in a system, A and B, and if A's rotation period is twice that of B's, then every time A completes a revolution around the Sun, B will have made exactly half a revolution. This periodic fit creates a resonance. The most famous orbital resonance occurs between Jupiter and its four large moons, especially Jupiter's Galilean moons, Europa, Galilee, Io, and Io. The orbital periods of these four moons are interconnected in some magical ratio, and together they form a classic resonance system. To give a simple example, the orbital periods of Io, Io4 and Iov show exactly a 3:2:1 ratio. In other words, while Io makes 3 revolutions around Jupiter, Io makes 2, and Io just completes 1. This wonderful synchronization not only allows these moons to maintain a stable orbit to avoid collision with each other, but also formed a cosmic ensemble, like a wonderful phenomenon. This resonance has a magical effect. It ensures that the gravitational interactions between the satellites are regular, so their orbits don't change drastically due to chaotic forces. You can think of it as 4 best friends playing soccer together, all playing at a pre-agreed rhythm and direction, and the game would be so orderly that there would be few accidents. Because their orbits are periodically aligned, the stability and harmony of the whole system is maintained. The magic of resonance is that it not only orders the gravitational relationship between these objects, but also somehow maintains the stability of the orbits. It is like a tuner that makes the orbits of celestial bodies more appropriate and smoother. Jupiter's moons, for example, help maintain their orbits through resonance. Without this resonance, the gravitational interference of moons such as Io and Io could cause their orbits to diverge or even lead to collisions. But because of the relationship between their orbital period, exactly an integer multiple of the relationship between these satellites become very regular movement, each other avoid, and their gravitational interactions will not make their orbits change drastically. This delicate balance makes their orbits remain amazingly stable. This balance is the result of the long-term evolution of the universe and allows us today to see these moons rotating leisurely around Jupiter, maintaining stable orbits for billions of years. Although Jupiter's moons are the most famous examples, orbital resonance is not uncommon throughout the universe. In fact, similar resonances can be found between many planets and their moons, and even between planets and planets. For example, there is also a famous orbital resonance between Neptune and Pluto. In this system, Pluto's rotational period is about one-third that of Neptune's, which means that there is a 3-to-2 ratio between Pluto's and Neptune's orbital periods. Although Pluto and Neptune sometimes approach each other, their orbits do not collide due to orbital resonance. Pluto's orbit is precisely designed to synchronize with Neptune's, and this resonance ensures that their orbits do not cross. The presence of this resonance has also made scientists realize that the celestial bodies in the universe do not exist in isolation, but are sustained and coordinated with each other through subtle gravitational and orbital relationships. The stability of celestial systems is greatly enhanced by this resonance, allowing them to maintain stable motions on long timescales. Understanding the phenomenon of orbital resonance is of vital importance to our exploration of the universe. In practical astronomical observations and space missions, scientists often utilize the laws of orbital resonance to design the flight paths of spacecraft. For example, many probes use orbital resonance to save fuel and glide to their destinations by using the gravitational pull of the planets, a strategy known as gravity assist. Further, by observing orbital resonances, astronomers have been able to hypothesize about the motions of objects in other planetary systems. For example, by studying the orbital resonances of Jupiter's moons, scientists have succeeded in understanding the interactions between Jupiter and these moons, which can also be used to speculate about the possible existence of orbital resonances in other planetary systems outside the solar system. 16. Cosmic dust. The dust of the universe is not just some tiny particles. It plays an extremely important role in the evolution of the universe, and almost every galaxy and every star is born without its participation. First of all, the dust of the universe does not mean the kind of dust we see on Earth. Cosmic dust is actually made up of tiny solid particles that can range in size from a few nanometers to a few micrometers. They are mainly made up of elements like carbon, silicon, oxygen, and iron, and some even contain organic matter, like hydrocarbons and amino acids. You can think of them as the raw materials of the universe. They help form new stars and planets, and even, at times, influence the temperature of the universe and the formation of galaxies. Most of these dust particles are found in interstellar space, especially in interstellar clouds and in the space between galaxies. Interstellar dust is not the usual floaters, but rather tiny particles that permeate the cosmic background. They also have a significant impact on astronomical observations and can even change the way light travels. A simple example, when we look at distant galaxies from Earth, we often find that their light looks a little fuzzy or dimmed, because these interstellar dust particles absorb or scatter some of the light. This phenomenon is called dust absorption. Its effect can even change the color of the objects we see, especially blue light, a shorter wavelength of light that is easily absorbed by dust. So when we look at a celestial object through a telescope, it's possible that the light we see is redder and dimmer than it actually is. But this dust also has a very important role to play, especially in the formation of stars. Can you imagine? These seemingly insignificant particles can play the role of coolant. During star formation, dust particles are involved in the cooling of the stellar cloud, or molecular cloud, as it is often called. A stellar cloud is a huge mixture of gas and dust, and when it collapses due to some external factor, such as a supernova outburst, it gradually gathers into a dense core that eventually forms a new star. But this process is not static. In order for this collapse process to go smoothly, the temperature must be gradually lowered. Otherwise, the gas and dust particles would be too hot to continue to gather. It is at this point that dust particles play a very important role. Scientists have found that dust particles help cool stellar clouds by absorbing heat from the gas and releasing that heat as radiation. Simply put, dust particles are like heat movers. They take the heat out of the gas so that the stellar cloud can continue to collapse at the right temperature and eventually give birth to new stars. In fact, the dust particles in this process are not only a cooling tool, but their very existence also has an impact on star formation. Studies have shown that interstellar dust can form complex chemical reactions between gases and other substances, thus promoting the synthesis of new chemical elements. Scientists have found that stars often absorb complex molecules from this dust before they are born, including even some of the precursors to biological molecules such as amino acids and sugars. As you can imagine, interstellar dust isn't just helping to cool things down, it could also be part of what drove the origin of life in the universe. This is why scientists believe that organic molecules, the seeds of life in the universe, may have started to exist as early as interstellar dust. That said, it's important to mention how interstellar dust is involved in the making of stars. During the birth of a star, dust and gas collide and absorb each other, slowly forming a huge vortex. The density at the center of this vortex increases and eventually coalesces into the shape of a star. These dust particles are important participants in the birth of stars. Interestingly, the fuel for the birth of stars is not pure hydrogen and helium, but also requires additional elements provided by the tiny particles in the dust. For example, heavy elements such as silicon and iron in the dust are essential for the formation of certain special types of stars. Scientists have observed through astronomical telescopes that when a star is about to be born, the surrounding ring of dust begins to gather and transform into a stellar disk. This disk-like structure is the predecessor of galaxies, planets, and even our own solar system. Dust is not just a coolant for stars, it is also a building material. For example, during the formation of the solar system, the initial solar cloud was a huge vortex of gas, dust, and ice, and over time, dust particles gradually gathered to form the planets, moons, and other celestial bodies we see today. Without the help of this dust, Earth, Jupiter, and even our Sun might not exist as they do today. Dust also helps planets form because of its accretion properties. When a star forms, dust particles swirl around it and begin to collide with each other. Over time, these dust particles merge into larger particles that eventually form protoplanetary bodies. An important part of this process is the mutual gravitational pull of the dust particles. When particles collide, they are held together by electrostatic forces. Although the gravitational pull of individual particles is weak, thousands of particles added together are enough to form a new object. Scientists have found that dust aggregation is not only dependent on gravity, it is also affected by air currents, light pressure, and other factors. For example, interstellar dust is subject to some complex interactions with stellar radiation. The accumulation and collision of these particles culminate in the formation of small protoplanetary bodies, which over millions of years grow larger and eventually form planets. Although cosmic dust plays a crucial role in the formation of stars and planets, they also have a different side to the universe that is not well known. For example, the dust storms we hear about on Earth are actually extreme dust phenomena. In some interstellar regions, the density of dust particles can be so high that they form huge dust clouds. These clouds can affect not only the birth of stars, but also the surrounding objects. When these clouds become very dense, they may even form a dust storm, which can block out the light of the surrounding stars and change the temperature and density of the entire nebula. Like dust storms on Earth, cosmic dust storms can sometimes completely change the appearance and evolutionary trajectory of celestial bodies. By observing different interstellar dust clouds, scientists have realized that these clouds may be the cradle of planets and even entire galaxies, and that their stormy processes may have prompted or prevented the birth of certain objects. 17. Stellar density of the Milky Way. Many people think that the Milky Way sounds like an infinite nebula with stars spread out like grains of sand. But if you think about it, the distribution and density of stars in the Milky Way and their relationship to the formation of life on our planet is one of the subtleties of the design of the universe. In other words, the density of stars in the Milky Way is just right, neither too sparse nor too dense, and it's like a carefully orchestrated balance that is just right to support the birth and evolution of life. Let's start with a broader context of just how big the Milky Way is and how its stellar density is distributed. The Milky Way is about 100,000 light-years across and contains about 200 billion to 400 billion stars. It seems like a huge number, but not every star here is close together. The stars of the Milky Way are not evenly distributed. They are more concentrated in the galactic disk, especially in the center of the galaxy. If you were to stand in a certain part of the galaxy, such as our own solar system, you would see that we have a relatively sparse distribution of stars, with an average of about a few stars per cubic light-year. Such distances don't allow the stars to affect each other too much or cause unnecessary radiation hazards. But, as it happens, the distribution of stars in the Milky Way is not disordered. You can think of it as a golden hourglass, with a relatively high density of stars in the central region of the Milky Way, forming a high-density region called the galactic nucleus, but one that is very far away, about 20,000 light-years away. Our solar system, on the other hand, happens to be in a seatbelt of the galactic disk, a region known as the galactic habitable zone, or habitable zone. This region is known as the Milky Way habitable zone. The density of stars in the Milky Way is just right, especially in our region, and it allows Earth to develop life in relatively favorable conditions. Our location, about 20,000 light-years from the center of the Milky Way, is at a point where the stars are relatively widely spaced. Imagine if we were near the center of the Milky Way. The density of stars in that place would be very high, and the strong gravitational interactions between stars could lead to severe radiation or celestial collision events, which would be very detrimental to the formation and stability of life. And if we're too far from the center of the Milky Way, we're faced with a scarcity of stars. That's because the formation of life requires a number of key elements, especially heavy elements. These heavy elements, including carbon, nitrogen, and oxygen, are often produced during nuclear fusion inside stars. Interstellar clouds of matter need to disperse these elements into the universe, either through explosions of stars, such as supernova outbursts, or by other means. And the star at the center of the Milky Way has been exploded many times to provide enough heavy elements that are essential for the birth of life. If our sun were in a region where stars are sparse, then there might not be enough heavy elements around us, and it would be difficult for life to emerge. Therefore, the sun is located in this position, can avoid too strong radiation, but also to ensure that the abundance of heavy elements is simply the golden position in the universe. The galactic habitable zone in which we live is like a perfect biological laboratory, which will not be destroyed by too much stellar radiation, nor will it be unable to harbor life due to a lack of material. We often hear scientists refer to the importance of heavy elements in the origin of life, which may seem like just a term for scientists, but in fact, it is closely related to the environment in which we live. Heavy elements are formed as a byproduct of nuclear fusion within stars, or as a byproduct of stellar evolution. When stars die, through supernova outbursts or planetary nebulae, etc., these heavy elements are released into the surrounding interstellar space and become the building blocks for the next generation of stars and planets. Without these heavy elements, the origin of life would have been difficult. Almost all of the elements necessary for life on Earth have been synthesized and released into interstellar space by these stars over billions of years of evolution. The formation of the solar system took place in just such an environment containing enough heavy elements. By analyzing star-forming and supernova-exploding regions, scientists have found that the Milky Way's habitable zone is the place where these heavy elements are in abundance. It provides enough material to support the complex chemical reactions of life without the radiation from stars threatening those reactions. This moderately dense environment provides an ideal place to experiment with life on our planet. Stellar density is not only about the abundance of matter for the environment of life where we are, but also about the intensity of radiation. Radiation from stars, especially high-energy ultraviolet, X-rays, etc., is very intense. If the density of stars in the Milky Way is too high, the radiation from the stars interacts with each other, bringing in large amounts of ionizing radiation. This radiation could not only destroy life that might be born, but also pose a serious threat to life that already exists. If we live in an area with a very high density of stars, the stars around us are like constantly erupting volcanoes with extremely high levels of radiation. Such an environment would be almost fatal to life. But fortunately, the Milky Way's star density isn't too high, and the distance between the stars is enough to allow the stellar radiation to be diluted. In other words, although our Sun is an active star emitting a lot of radiation, its radiation does not have a devastating effect on the Earth, and life on Earth can survive with the protection of its atmosphere. The distribution of stars in the Milky Way provides us with a very ideal environment. We are located just enough to avoid the threat of high radiation and enjoy the right amount of stellar radiation, which is essential for the formation and stable development of life. Scientists' study of the density of stars in the Milky Way dates back to astronomical breakthroughs in the last century. With advances in telescope technology, astronomers have come to realize that the stars in the Milky Way are not uniformly distributed as initially thought, but have a well-defined hierarchical structure. An interesting discovery was that the densest stellar regions in the Milky Way are not those near the center of the galaxy, but rather in certain specific bands of the galactic disk, which have a moderate density of stars that provide an abundance of heavy elements around them without being so dense as to trigger excessive radiation. This discovery surprised scientists, and some have even called it a cosmic coincidence, because the Milky Way's stellar density provides ideal conditions for the emergence of life. Scientists believe that the structure of the Milky Way was gradually formed through billions of years of stellar evolution and the evolution of interstellar material, and, even to some extent, this environment may be difficult to replicate in other galaxies. There are many types of galaxies in the universe, some of which are very densely packed with stars, like elliptical galaxies, whose stars are densely packed in almost every corner, while others are relatively sparse, like some irregular galaxies. The Milky Way, on the other hand, sits right in between, creating an environment that lends itself to both an abundance of heavy elements and an avoidance of deadly radiation. 18. The special chemical properties of carbon. If we imagine life on Earth as a grandiose building, then carbon is undoubtedly that most important and clever architect. It's not the most powerful atom, or even the most common element, but it has a special ability that allows it to build the complex and delicate molecular structures necessary for life. Have you ever imagined that? All the DNA, proteins, sugars, fats, etc. on the entire planet, almost all of the keys to life's activities are dependent on carbon. What makes carbon special is first and foremost its atomic structure. We know that an atom is made up of a nucleus containing protons and neutrons, and electrons that move around the nucleus. Carbon has 6 protons in its nucleus and 6 electrons. Because it has only 4 outer electrons, this gives it unrivaled flexibility. Simply put, carbon is very social. It always likes to make connections with other atoms, especially with other carbon atoms. It can share electrons and form stable bonds with other atoms through covalent bonding, which allows it to form long chains, rings, and even complex webs. It is important to realize that these bonds in carbon are very stable and can withstand the test of time. Because of this, carbon is the cornerstone of the building of life. For example, if we compare carbon to a person who is very good at doing jigsaw puzzles, it is not only able to put together simple shapes, but it is also able to put together countless complex patterns. For example, the structure of the DNA double helix is made up of a series of carbon atoms connected by covalent bonds, and it is these stable structures that ensure that genetic information can be transmitted precisely. The magic of carbon is also reflected in its ability to form a wide variety of chemical structures. The simplest, of course, is the carbon chain. In a carbon chain, each carbon atom and the surrounding carbon atoms are connected by single, double, or triple bonds to form the common hydrocarbons we see, e.g. methane, ethylene, etc. These chains can be linear or branching, and, even under certain conditions, carbon chains can wrap around into a ring-like structure, like a tiny candy. But interestingly, carbon can form not only these chains and rings, but also three-dimensional mesh structures in extremely complex environments. For example, graphite and diamond. In graphite, the carbon atoms are arranged in a flat, hexagonal network, like a sheet of ultra-thin paper, while in diamond, The carbon atoms form a three-dimensional, solid structure that is one of the hardest substances in nature. Can you imagine? An atom that can look so many different ways at once. This is the unique charm of carbon, whose chemical properties allow it to adapt to a wide variety of biological environments, from inside the cells of microorganisms to between every cell in our bodies. It builds the building blocks of life with precision. Life is made up of a large number of complex molecules, and most of these molecules are made up of elements such as carbon, hydrogen, oxygen, and nitrogen. However, it is the special properties of carbon that allow these molecules to achieve complex structures. Of all the molecules of life, DNA is probably the best known, and it is the carrier of all our genetic information. So what exactly does DNA have to do with carbon? We can think of DNA as a book in which all the stories of life are recorded. The paper of this book is carbon, and the basic unit of DNA is a nucleotide, and each nucleotide contains a sugar molecule, a phosphate group, and a base. Each nucleotide contains a sugar molecule, a phosphate group, and a base, and the connection between the sugar molecule and the phosphate group is formed by carbon atoms. In fact, sugar molecules, such as deoxyribose, are themselves made up of carbon atoms. As you can see, almost every part of the entire DNA structure is made without the involvement of carbon. Then look at proteins. Proteins are made up of amino acids, and within each amino acid molecule, carbon atoms play an important role. Proteins are like a jigsaw puzzle, in which each amino acid molecule is linked together by carbon atoms to form a complex three-dimensional structure. These structures give proteins their unique functions, such as enzymes that catalyze chemical reactions, hemoglobin that transports oxygen, and structural proteins that build cells. Without carbon, these complex structures of life simply could not form. The magic of carbon is not only in its ability to build the basic building blocks of life, but also in its ability to evolve over time and in response to changes in the environment to produce a wide variety of life forms. There's a key factor behind this evolution: carbon's flexibility. As an example, early life forms may have been simple single-celled organisms that relied on carbon atoms to build simple molecules to survive. But as life gradually evolved, carbon flexed its creative muscles, forming increasingly complex molecular and cellular structures. For example, early life forms may have relied on a process called anaerobic respiration for energy, but with the involvement of carbon and the advent of photosynthesis, oxygen became available on Earth. The advent of oxygen in turn fueled the evolution of aerobic organisms, allowing life to access more energy and eventually evolve into complex multicellular organisms like us. Carbon is not just the main protagonist of life on Earth, it may also be the common language of life in the universe. Scientists hypothesize that carbon is a common element in nebulae, and that processes such as the birth and death of stars and supernova outbursts provide the conditions for carbon to be made in the universe. These carbon atoms could eventually float to other planets, opening up the possibility of extraterrestrial life. In fact, scientists have already found signs of carbon in the atmosphere of some planets, which means that carbon may not only be the cornerstone of life on Earth, it may even evolve its own life on other planets. Carbon's special chemical properties have not only shaped life's past, but are also shaping the future. Scientists are now investigating how carbon-based molecules can help us solve some of the planet's most difficult problems, such as carbon capture technology to reduce greenhouse gas emissions, or synthetic carbon nanotubes and graphene to create stronger, lighter, and more flexible materials. In short, carbon is not only the element of life, it is also a mysterious designer of life. It uses its own special ability to turn simple molecular structures into complex, delicate networks of life. This amazing ability is what allows us to survive, evolve, and create the future on this planet. Well, that's it for this installment. Likes and comments welcome. Thanks for watching.